Welcome to the Control Seminar. Today's guest is Herschel Pangborn, colleague and friend of mine over at Penn State. Give you a little bit of a bio here before we kick off the talk. So Herschel, he's on faculty over at Penn State Mechanical Engineering, Mechanical Engineering and Aerospace Engineering by courtesy at Penn State. He got his bachelor's degree actually from Penn State in 2013, and then he went over to UIUC, Urbana-Champaign, worked with Andrew Aline for his master's and PhD in 2015 and 2019, respectively. His research interests are in the areas of MPC, optimization, set-based verification of dynamic systems, and those include electrothermal systems in vehicles, buildings, and power grids, and is recipient of a couple of awards, at least maybe more than a couple, but a couple that he's mentioned in the bio here. I was a faculty fellow with the Air Force Laboratory. That was in 2020, and then very recently, received the ONR Young Investigator Award. So let's please welcome Herschel Pangborn.
Great. Thanks so much. Thanks for hosting me and the introduction, Chris. And it's really great to be here and honored to speak at your seminar series. So yeah, I'm Herschel, and there's a couple different seminar talks I could give. I chose to focus this one on what is the most theoretical area of my lab right now, which is these set-theoretic methods. Quick introduction to my lab to get started. If I can get it to advance slides, there we go. So broadly, we work at the intersection of dynamic systems and control with a lot of applications to energy systems, but not exclusively those. The lab's about 15 students, about a third are PhD, a third are masters, and a third are undergraduates. And we're fortunate to have sponsorship from a wide range of sponsors, government sponsors, as well as companies in the aerospace industry and elsewhere. So I'll give you, before we jump into the set-based methods, I thought I would give kind of some quick vignettes of the things that I'm not going to talk about a ton, right? So we'll do like a 5-minute recap of the energy systems part of my research, and then we'll spend the rest of the time on the set-based methods. And those two things converge a little bit, and that'll come towards the end. So we work really at the highest system level of coordinating the energy systems of vehicles and grids. So you think about an aircraft, right? You have the engine, you have electrical systems, you have thermal management systems, you have hydraulic systems, right? Those all have to be controlled. They span a wide range of different energy domains, as well as a really wide range of energy timescales, right? So you have tanks that might heat up and cool down over hours, but then you also have sub-millisecond electrical transients to deal with. And so we work on developing frameworks that can model across these different timescales, and then we can exploit the knowledge of those models for system design as well as for controls. We often find these systems are so complex that we can't just have one centralized controller that makes all the decisions across all the timescales. And so we decompose the decision-making across networks of predictive control algorithms that exchange information to communicate and coordinate their actions. For the modeling side, one representation we found is really useful is to use graphs. And so here we're showing kind of a notional hybrid electric aircraft system, right? It's got an engine, a battery, right? The electrical systems, and then thermal management to cool everything. And if you just look at where do you store energy in this system across various domains, you can model that conservation as a graph. And then we can write a really nice differential equation that tells us about how the dynamics of this energy system will evolve as a function of the graph topology. And that's that matrix M is the basically the adjacency matrix, actually an incidence matrix, but it's the same idea as an adjacency matrix of a graph that tells us about the connections within the system. And we've kind of highlighted each individual component here, right? So this is a really nice modular way to build up a model of an energy system across all of its constituent domains and timescales. Then we take those models and we apply things like model predictive control to them. I'm not going to talk a ton about the basics of MPC because I think most of you already know how MPC works, right? You take a dynamic model and a set of constraints and you optimize a cost function over a receding horizon. And this is really nice for energy systems, right? For example, on the thermal side, we can do things like pre-cool. So if I know I have a big heat load hitting my system soon, which is what that top profile is, then I can take actions to start cooling it off in advance. Right, that's what we're doing here to the temperature of a thermal bay, whereas a standard kind of reactive feedback controller would not be able to cool in advance and results in a big excursion above a temperature limit. Now, these energy systems tend to be very nonlinear. Here, my prediction model up at the top left, that's a linear state space model. And so we've worked a lot on better ways to apply controls given that our dynamics are very nonlinear. We don't necessarily just want to do nonlinear MPC straight up because those optimization problems can be really tough to solve in real time, especially when you're computational power limited, right? You're trying to run this on flight controllers or let's say embedded hardware that would be used for flight. So you usually wind up doing some kind of linearization. That could be a Taylor series linearization, for example. But what we found is that Taylor linearization, it works well about the point where you linearize, but it really doesn't hold up over a prediction horizon for these nonlinear systems. Right? As you propagate the system, maybe tens of seconds into the future, the Taylor linearized model kind of falls apart as you get away from the point of linearization. So instead, we've turned to these methods that combine physics and data to perform a linearization. This is kind of like Koopman operator approaches, if you've heard of those. Right? The idea is that you can represent a nonlinear model as linear, but in a lifted higher dimensional space. And so what we do is we keep the physical states that we get from our graph and from conservation of energy. And then where there are nonlinear power flows, we lift and add additional states whose dynamics are learned from data to capture or approximate those nonlinearities. And so we found that this does a really nice job of giving us global linear approximations of nonlinear systems that hold up over a long prediction horizon. And they preserve things like conservation of energy, which is really nice as someone who does energy systems to know that our controller is aware of conservation of energy. Here's a result we did. It's interesting. This is blue on my computer, but then it kind of becomes a black line on the projector, but that's fine. So here's an example we did in simulation on a thermal management system. And then it took us about a year to figure out how to do this experimentally, but we did get it done, right? So this is a single-phase thermal test bed we built in our lab that's designed to be easily reconfigurable. So we're generating heat and cooling it down and storing it in different places. And we showed that our lifted linearization approach outperforms a Taylor approach. In these plots, lower bars are better, right? That's better satisfaction of constraints. And so you can see at short prediction horizons, the Taylor approach actually does better because it's linearized right about the current operation, and that holds up well over a short horizon. But as you get to longer horizons, Taylor approaches actually, in some cases, kind of start improving and then start doing worse again because the model falls apart, whereas our lifted graphs just continue doing better and better for longer horizons. And then again, we can't do this with centralized control often because there's just so many different timescales and energy domains going on. So when we have something like an integrated mechanical thermal electrical system, we create a network of hierarchical controllers that coordinate their actions. And that's what we're showing here. So we have a hybrid electric vehicle test bed that has basically like a lawnmower engine coupled to a battery driving a dyno. And then we couple that to our thermal management system, designed a whole hierarchical structure with multiple predictive controllers all working together. And we showed that we could run the system both more efficiently and much more reliably than a conventional controller would do. All right, so that's kind of a very quick overview of the half of my research portfolio that I'm not going to talk about a lot for the rest of the talk. And now let's get into the stuff I do want to talk about. So this is what I'm calling set-theoretical methods for safety-assured autonomy. Right? There's two pieces to this. There's kind of what you can do offline, things like verifying the control of a neural network. And then there's what you can do online with these methods. And we'll talk about some autonomous vehicle motion planning there. Right? You can see here we've got a simulation of an MPC that's driving a vehicle through an obstacle that happens to spell out the letters of my school, right? PSU. So if we think about set-theoretic methods, what do I mean by that? A good way to think about this is in terms of reachability analysis, right? So the idea is imagine that you are flying a vehicle, you have some initial starting set, and your goal is to get inside of a target set after some period of time. Along the way, you want to avoid some unsafe set, and maybe there's some set of disturbances that are going to try to push you into that unsafe set. And so the goal of reachability is to check whether all trajectories of your system from your initial set will be safe, meaning that they will not intersect your unsafe set and that they will achieve the desired performance of getting inside of your reachable set. And so you could check this through just running a ton of simulations, right? You could pick points randomly inside of your initial sets and propagate the dynamics of your system, right, in open loop or closed loop. and see if you tend to get into the target set and avoid the unsafe set. But that doesn't have any real inherent guarantees, and typically you'll tend to miss the most dangerous points, the most extremal points. Of course, there's lots of different ways to do stochastic methods, and so I don't want to discount those, but what we're going to focus on here are ways of calculating these envelopes as sets, right? So we want to get a set description, right, of this kind of funnel that leads you to your target set or your final reachable set. So let's look at a simple example that's a little easier to understand. So let's say you have a dynamic system that is, has two states and has a switch in it. So when we cross this guard along the center line, right, your system will go to one of two equilibria, and so we propagate it forward from some initial point. You can see you kind of bifurcate across this guard and continue, right? We call the process of calculating these sets forward reachability. For that, we use a successor set operation. So this basically maps you from a set at time step k to a set at time step k plus 1, and you can do that subject to a system model, which is this F, as well as sets of inputs and disturbances. Again, this could be an open loop system, or we could plug in a particular solution for the controller and propagate a closed loop system. All right, and you can also go backwards. So we could start at the equilibria and try to ask, from what points would I reach this equilibria? And what you can see is for this system, right, you can actually reach that equilibrium from both sides of the guard. Right, and so this would be the precursor or predecessor set. Right here, we're going from a set at step k plus 1 backwards to a set at step k, and you just iterate over this operation to go as many steps backwards as you want. So if we're going to try to calculate these sets, really the first question we should ask ourselves is, what's the mathematical representation to use for a set? Right, and there's a lot of choices. I could use intervals, right, basically boxes. You could use ellipsoids. You could use various description of polytopes. We'll get to the zonotopy stuff in a little bit. Here's an example of a vertex representation polytope, right? So in vertex representation, we literally just save the vertices, and then you take the convex combinations of those. We could equivalently use a half-rep polytope, which is where we would basically record inequalities for the line segments that tell you which side of each of those segments you're on. And the way you choose a set representation is based on what operations you need to perform, what the complexity of those are, both in terms of computational complexity and the memory complexity of what you have to store. So let's start by looking at the computational complexity side. And I listed out, not all the operations we could need, but some common ones. And here we're looking at how hard are those operations, right? So some of them are polynomial, which would include potentially linear in complexity, right? Some are exponential, and some you can't do at all if you want to preserve the same representation, right? So for example, if I want to take the union of two ellipsoids, that doesn't necessarily give me an ellipsoid back, and so we'd say that that operation is not closed. Now in particular, right, you can see that zonotopes, right, they've got some greens. Constrained zonotopes have a lot of greens, except they're not closed under unions. So maybe just based on this one table, they're kind of looking promising. But you may or may not know what a zonotope is or a constrained zonotope is. So let's do a little bit of zonotope 101. Does anyone, maybe by show of hands, like who has seen zonotopes before? Just, okay, maybe a third of you, which is good. So here's what a zonotope is, right? Take a unit hypercube. Think of this like a box, right? And so take all points in a box and then scale them by some matrix G, and then shift them by some center C. That's all they are, right? So for example, we could do a simple 2D example like you see there, right? Here's the matrix. I'm going to multiply that box by, right? And then we shift it by its center. So this is a really nice way to compactly represent sets. And as we saw previously, right, gives us some really nice efficient operations. The challenge with zonotopes is they have to have this symmetry property, right? They have to be centrally symmetric. So in 2016, some really clever folks figured out that you could kind of correct that flaw by adding a set of equality constraints on the factors, right? Factors meaning that box, right? The factors are what define that hypercube, right? So here, instead of living, in anywhere in this hypercube. Now we've constrained these factors, right? Where in this case, they have to live on this plane within the hypercube. And then we take those and we scale them and we shift them, right? Or really, we map them through G, right? And then we shift them by the center. And now we can represent any polytope, right? So we can represent polytopes with half-space representation or vertex representation. And now there's also a constrained zonotope representation equivalently of a polytope, right? But again, we get lots more greens here than we do in these other representations that we can use for polytopes. All right, so let's go back to our system that has two states and switching, right? So this is a slightly different system, but same idea, right? We're going to switch it across a guard. And so you start up here to the left, you propagate for a few steps, and part of your set crosses the guard, right? So now some of your set is going to follow one set of equations, the other is going to follow a different set of equations, and it's going to go in two different directions, right? That's not going to be a polytope anymore. So what do? Well, one option is you just split the set into two polytopes, right? And this one you propagate forward through its dynamics, and that one you propagate through its dynamics. That's fine, right? You propagate that one step. Oh, both of those cross the guard again. So now you're going to split it again, right? And this keeps happening over and over. And so what you see is if you just keep doing this splitting, you wind up having to track an exponentially increasing number of convex sets potentially, right? So that means you're both having to do the calculations to propagate all these sets, and then you're also having to store all of them in memory. All right, and that gets to be pretty painful to do. So when we have these convex sets, they just don't work well with hybrid systems. So some colleagues and I spent a while trying to figure out how to address these. And eventually what we figured out we needed to do was add some binary variables to the representation of the set itself. And so we call that a hybrid zonotope, right? I call this in the slide a new set representation, but maybe it's more like new-ish because it's been out for a couple of years at this point. But basically the idea of these is that we still have those factors that live in the hypercube, but now we also add a second dimension of them stacked on that are binary variables, right? Either -1 or 1. And so what that allows us to do is basically embed 2 to the NB convex sets using only NB of these binary variables inside our set representation, right? So you can get multiple disjoint regions in your factor space, and then those can map to multiple convex sets, all captured within a single set representation. And what's really cool about this is that hybrid zonotopes preserve the greens all the way along. So all these set operations for them are still very computationally easy to do. And we can even do unions, right? Because I could take the union of 2 completely disjoint convex sets and just represent them both within a single hybrid zonotope. Here's some examples. For a while, my grad students got really into chess. And so they figured out how to represent one color of squares on a chessboard as a hybrid zonotope. And you can do it very compactly, right? You just need a couple of binary variables, and the center winds up being 0 and the constraints. And so you can represent all 32 convex sets, right, that are the kind of tan squares here, just using 5 binary variables. Here's a much more complex example. So this is just a random hybrid zonotope that has 20 of these binary factors in them. And so this could represent potentially 2 to the 20, the union of 2 to the 20 convex sets, right, which is like 10 million potential convex sets. But it turns out a lot of them wind up being empty. And so there's actually a little more than 1,000 that are not empty. Figuring out how to plot these took us quite a bit of time, how to plot them efficiently. But now we've got it down where a set like this takes us about a minute to plot with MATLAB, right? It requires doing some mixed integer optimization to figure out which of those 10 million possible sets are empty or non-empty. But there's some good algorithms we can use for this. So again, we have a set that can represent unions of convex sets very efficiently by embedding the exponential complexity of the number of sets within just a linear number of binary factors. And so what I want to argue is that these hybrid zonotopes provide a very unifying, kind of broadly applicable framework for performing analysis of complex types of dynamic systems. right? And I'll give you examples for 4 specific types of systems. One over on the left is mixed linear dynamical or piecewise affine systems. We'll do an example of MPC in closed loop where we can propagate reachable sets of MPC. We'll show you how we can do reachability of neural networks in open and closed loop, and even some approximations of nonlinear systems. And I guess shameless plug, we wrote a MATLAB toolbox that has some nice classes for creating hybrid zonotopes, converting different set representations, and some good examples for these different classes of reachability problems. So if you're interested, you can check out that toolbox. We call it ZonoLab because it's in MATLAB. And we're also working on a different set of tools that will be designed to bridge towards real-time applications for this. So those are in C++ with Python bindings, and we'll work in ROS2. And we haven't released them soon, but they're on the way. Or we haven't released them yet, but they'll be on the way soon. I'll show you some examples today that will use that. So here's how we get that expressiveness, right? The key thing is to build what we call a set-based mapping as a hybrid zonotope, right? And what this does is it basically embeds the successor set identity in a set that stacks the dimensions of step k on top of the dimensions at the next step, k plus 1. In this case, I'm showing it with some controller in the loop. Again, we can do this in open loop or closed loop. We can do it with or without disturbances, right? There's lots of degrees of freedom there. The second line is just saying that it's valid in some domain, right, of initial states. You have to figure out when you build this mapping, where do you want it to be valid? So to make this more concrete, I guess we'll get to a concrete example next. Let's talk about this first. So let's say you have some input set, right, that you're going to be your set of states at time step k, and you want to map those to see where they'll go at time step k plus 1, right? If you have created this mapping of that system's dynamics, all you have to do is take a generalized intersection with that input set, and then you do a linear mapping onto basically onto the dimensions of the next time step of the output. Right? Those operations scale linearly with the dimension of the system. They scale linearly in time. And we can furthermore build these set-based mappings pretty efficiently, as I'll show you. And so this gives you a really nice way to map these potentially hybrid or nonlinear systems through their dynamics as sets. So here's an example, right? Let's say I am dealing with a ReLU neural network. It turns out because these networks, the activations function is just piecewise linear. So I can embed that exactly in a hybrid zonotope. So I get an exact representation of a neural network. And here's what that mapping might look like. So here I'm going to call the input step x1 and x2. And then we're saying that's mapping to an output y hat. So I'm changing my notation a little bit, but it's not too tough to follow. All right. And so I want to know, for some input set for x1 and x2, what are all the set of all outputs that could reach? And I just have to do this generalized intersection and then linear mapping using our hybrid zonotope set-based map. And you can do this in that direction. You can also go backwards. So I could say, let's just take the part of my map that gives me a positive output, and I want to know what inputs could get me there. And so we just flip the directions of the generalized intersection and the linear mapping, and we can do essentially a backwards reachability. All right, same computational cost. So let's go through some, still toy examples, but slightly more complex. So this one is what we call a mixed logical dynamical system. You could also represent it as a piecewise affine system. And so think of this as like an overhead view of a building that has 6 rooms, and we're modeling the temperatures in the rooms. They're exchanging heat with each other and also heat with the environment. And 2 of the rooms have heaters in them, and those heaters are turning on and off thermostatically, right? Just based on when you hit certain temperature limits. We're going to treat the discrete time representation of this system as our plant, and then do reachability analysis with it. And so we start here, it has 6 states, so we can't plot all 6 at once. So we're kind of plotting cross sections of 2 states at a time. And you can see different parts of the states hit the switching regions for those thermostats at different times. And so you get this splitting of the sets into thousands of individual pieces. So if you propagate these with hybrid zonotopes, it takes less than a second if you don't do any reduction techniques along the way. We have some order reduction techniques we can use, and if you apply those, it takes about 10 seconds. And then it requires you to store this many variables to represent that final set, right? So there's a lot of generators to keep track of, but it's not too bad with a computer, right? If instead you do the approach we talked about earlier, where you use convex sets and you just keep splitting them and propagating them, right? You wind up taking at least 10 times longer, and you have to store, tens of thousands of variables in memory. So you can see kind of the compactness of hybrid zonotopes representing the same set, but in a much more compact way, and then also giving you access to more efficient calculations. And just to prove that this is a reachable set, we simulated a bunch of individual trajectories and plotted them as these green points. And what you can see is they kind of cluster in the interior of the set. So this is why just this random sampling, right, tends to give you points inside the set. It doesn't give you the extremal ones, whereas set-based reachability is a more exhaustive verification. And again, we can go backwards as well. So here we started at some ending temperature and then propagated this backwards and said, what are all the initial temperatures 50 steps earlier that would get me to this ending temperature? And when we did that, our approach was 600 times faster, and again, had just a small fraction of the number of variables to store in memory. All right, so that's kind of a logical system with some switching. How about MPC? So those of you who have studied MPC, might know that the explicit solution of an MPC problem with a quadratic cost and a linear model, right? You can solve optimization programs to get those control laws explicitly. What we did is we basically took the KKT conditions that define the solution of that MPC formulation, and we embedded those conditions directly in a hybrid zope representation, and then we can propagate that representation through reachability. We don't even have to do any optimization, right? So we can calculate implicitly the reachable sets of MPC. We don't have to solve any optimization problems. Now, if you want to plot them, then you have to solve an optimization problem so you know what to plot. But you can propagate them without doing that, right? And we've shown that this works well. You can go forwards. Again, you can go backwards. It's a nice way to verify an MPC formulation after the fact. So instead of adding extra constraints, maybe terminal sets, those kinds of things, in order to get guarantees, those introduce conservatism into the controller. Another approach is you just formulate the controller for performance and then do reachability and check if it stays inside your safe set before it converges to a stable point. And that's another way to check if it's stable. How about nonlinear systems? So we don't do nonlinear system reachability exactly with hybrid zonotopes, but we can do it approximately by basically just using piecewise linear approximations. So for example, take a sine wave and approximate it with just some line segments. You can approximate it arbitrarily tightly just by adding more and more line segments, right? And we call those line segments a special ordered set representation that comes from the literature, right? Then you just bloat that in order to over approximate the sine wave, right? And you have yourself an over approximation of a nonlinear function. And we've written a bunch of papers on extending that from simple nonlinearities to more complex systems. Really, the key is, rather than, if you have some higher dimensional, more complex nonlinearity, rather than trying to approximate that directly in all its dimensions, which can be really computationally tough, what you do is you decompose it into its constituent functions of maybe just one or two variables. You approximate each of those as a hybrid zonotope, and then you recombine the hybrid zonotopes. And if you do that well, then you can get really nice tight over approximations of nonlinearities. They don't necessarily have to be super complex in terms of the number of variables that you have to store. So to show that to you, let's do a closed loop example. So here we took a nonlinear MPC of a pendulum, used it to generate some training data, trained a neural network to mimic the control laws of that MPC, created one of those set-based mappings of our neural network, which is plotted up here, right? So we can represent, that's a ReLU neural network, so we can represent its input-output behavior exactly with hybrid zonotopes. Then we over-approximated the dynamics of a inverted pendulum in open loop. And then we just kind of intersect those two maps together to form a hybrid zonotope map of the closed loop dynamics. And then we can do reachability of our closed loop system using that. So here's what that plot looks like, right? We start with a kind of a wide range in initial positions and run it forward, and you can see that you stabilize the inverted pendulum. All right, each step of propagation takes about 5 milliseconds. Plotting it takes longer, but if all we care about is just knowing if it's bounded in a particular direction, we can solve the mixed integer problem for that pretty quick. So this inverted pendulum problem is actually a benchmark problem used for this kind of really fun competition they do. They call it a friendly competition. That's the ARCH competition. So every year, a bunch of different teams, they solve these benchmarks, they send in their code in a report, and then they write up a nice compiled document that summarizes all the tools. So recently, there have been 4 tools that solved these, the reachability of these inverted pendulums controlled by a neural network. We did, we modified the example a little bit in order to facilitate a good comparison, and so that is documented in this journal paper. But basically, if you look at the way that they define the initial set from which to perform reachability, in this competition, right, they use a very small initial set, right? You can see that both the position and the velocity are just a width of 0.2. And if you start from that small initial set, the tools out there tend to work pretty well, right? Ours actually takes quite a bit longer. But if you then take that initial set and make it bigger, a lot of the tools out there fall apart. And that's because they're trying to also do over approximations of these nonlinear systems, right? But that approximation is more coarse, and so you get, they call it wrapping error, kind of more and more error each step that builds on itself, and eventually things just explode. But with hybrid zonotopes, because we can approximate these nonlinear dynamics arbitrarily tightly, right, we're able to solve these problems. Again, it's not fast, but at least it works. What you would have to do with these other tools, basically the option with these other tools is you can take this large set and you can split it up into potentially hundreds of smaller pieces and run all of them individually. But that really only works in a small dimension, and figuring out how many pieces to split it into is a challenge. So we like the hybrid zonotopes. We can do this as a single process. Here's another kind of neat example. So here we have a vertical collision avoidance system. So 2 aircraft flying at each other, right? You're trying to adjust the height of one so that they don't crash into each other. So you have a pretty simple representation of the dynamics, but then the decision making is driven by 9 neural networks. Each has about 100 neurons. And so those look at the states, they provide an advisory, and then the pilot has a choice of several actions they can take based on which neural network wins out, right? So you have a dynamic system, you have a bunch of neural networks, and then you have switching logic to select between these different options. And so with hybrid zonotopes, we can prove in about a second that this controller is not safe, right? In fact, it would cause the aircraft to violate their separation requirements. None of the other tools that have tackled this problem, they do provide solutions, but they have to do some modification of the problem statement because it just has too many different classes of things at once, right? Again, dynamics, neural networks, logic, right? We can embed all those things very naturally with hybrid zonotopes. All right, so that's kind of the offline verification part of the talk. About a year ago, we started thinking about whether there could be a way to use hybrid zonotopes online. And we tried to find a good representative problem to play around with to do this, right? Some kind of online controls problem where there would be a lot of nice non-convexities to tackle. And we settled on autonomous vehicle path and motion planning as our problem. So I'm an energy systems person, right? I'm not an autonomous vehicles expert necessarily, but we had a tool that we thought could provide impact in this application. And it turns out that it works pretty well, right? So our goal here is to solve MPC-based motion planning problems in non-convex obstacle fields, right? So I have some obstacles here, which are these black areas. The area where I'm allowed to be then becomes a non-convex space. And so that requires solving a mixed integer optimization problem. And we wanted to see if hybrid zonotopes would provide some benefit in these sorts of cases. So again, we can represent an exponential number of polytopes with just a linear number of variables inside hybrid zonotopes. Right here, we are just showing an example. So we have 3 obstacles, and then we decompose the free space into polytopes, and we can represent those as a single hybrid zonotope. And then we wrote our own custom mixed integer solver to exploit the structure of this optimization problem for a fast solution. And I'll just cite the papers we've written all here in case you're interested in them. We use a couple of different ways to generate these maps. So one is, if you represent your obstacles as polytopes, again, you can use these existing algorithms to partition the space and then recombine them into hybrid zonotopes. And you get a very well-defined complexity in your hybrid zonotope in terms of how many regions there are, and in this case, how many vertices are used to define the polytopes of the free space. Another way to build a map is to use a grid. And this, my understanding is, this is pretty commonly done, right? So you just grid your space and looked at which grids have something in them you want to avoid and which grids are free. And this works very well with hybrid zonotopes, kind of like that chessboard, because we get very few continuous factors inequality constraints and a reasonable number of binary variables to optimize over. One of the benefits we get from our hybrid zonotopes is that they have tight or sharp convex relaxations. So when you go to solve mixed integer optimization problems with branch and bound, what you wind up doing is you relax binary variables. So instead of being 0 or 1, you relax them to be between 0 and 1, and then you solve in our case, a quadratic subproblem based on that relaxation. And the tighter that relaxation is, the better a bound you get in your optimization, which allows the optimization problem to go much quicker, right? So if you use kind of a standard way of tying together these sets, which is called a big M representation, right, you get very poor bounds in some cases. So here, this kind of light purple area is just an example hybrid zonotope. If you create that with big M and then you relax it, you get this massive red area, right? But if you use our method with hybrid zonotopes, right, you actually get the convex hull of that hybrid zonotope. And so that gives you a much tighter bound in your optimization, which allows it to proceed more efficiently, right? The other thing you get is when you relax the binary variables in a hybrid zonotope, it gives you a constrained zonotope. Those constraints are boxes, and then it reduces the number of factorizations you have to do under the hood of the optimization. And so that's a further benefit to the speed. Another place you can get speed is just kind of using the context of a motion planning problem, right? So we have basically one binary variable associated with each polytope in the free space. And you know something about the sequencing of those binary variables over the horizon of your problem, right? I'm not going to jump from one side of the map all the way to the other side of the map unless my vehicle can go fast enough to get there between time steps. And so we can constrain the branching in our branch and bound, right, over time just based on the maximum speed of the vehicle and where you can actually reach, right? Both from the current location of the vehicle to different regions, and then also from one region to the other regions. And so we can this is like a really coarse notion of reachability just based on an assumed maximum speed. And we can leverage that to get some sparsity in the algorithms that help to search for an optimization. So here's some examples for 5 different maps. We have one that has all convex obstacles, one that has a non-convex obstacle, an occupancy grid. This one has both hard obstacles as well as regions that have an elevated cost. We'll talk about that more later. And then we have a 3D grid. All right, so we can solve all of these with our mixed integer motion planner, and we solve them really efficiently. So here, what we're comparing these bars, the top here is an average solution time, right? The bottom is a maximum solution time. And as you go across from A to E, these are the 5 example maps I showed you. And then we're looking at the left bars in each grouping are our approach with and without a warm start. And then the middle one is our approach using a half-space representation. And then the right bars, the kind of reddish ones, are using a commercial tool called Gurobi, which is kind of the state of the art in general purpose mixed integer optimization. So we wrote our solver in C++, right? Called it from a desktop computer, tried to get as much parity as we could with the implementation in Gurobi, and wound up being orders of magnitude faster, right? And granted, like, we're solving a much more specific type of optimization problem where we can leverage the structure of that. So we're not as general as Gurobi, right? But for the problem we're solving, it's much faster. It also seems to be more scalable, in particular with the duration of the horizon. So here we picked just one of those maps, and we solved it with 5, 10, 15, and 20 step horizons in our MPC prediction. And you can see, the Gurobi approaches are growing quite significantly in their computation time, right? And ours, it starts out kind of below the rounding error, right? And then even at the end, it's just barely above that. So seems to scale empirically really well with increasing horizon. So that was on a desktop computer. What about on an embedded machine? So we bought an NVIDIA Jetson. We actually, built this open source car, but that has a Jetson on it. So we wanted to see if this would run on the Jetson. Set up our code to be called from ROS, and fixed it to run at 5 hertz. Sometimes that requires executing a little early before it's gone all the way to optimization. But what we found is you can get pretty reliable solutions at 5 hertz. Here, these plots are showing the global optimum as well as the best solutions we got when we constrained to run with a processor in the loop at 5 hertz. And there's basically negligible differences, right? For example, in this one, one goes to the left around this obstacle, one goes to the right, but it's kind of a wash anyway, right? So this works well in real time. I wanted to expand on this risk-aware planning. So you can imagine a context where maybe you're trying to avoid some adversary, right? They have radars, and then there are obstacles on the map that block those radar. And so you can try to hide in the shadows of the radar. And so we associate risks of detections with different areas in our grid. One way you could do this, not the only way by far, but one way you could do it is just threshold. And so I'm going to stay outside of regions that have above a certain risk. But that could mean that you completely cut off corridors and then can't get to your goal at all. It also means that if you threshold, now you're kind of weighing everything equally, right? You're not weighing different regions by different amounts anymore. So within our MPC formulation, we kind of for free get the ability to associate different costs with being in different regions. And then we can solve a risk-aware MPC formulation for our path planning through the map. So that's kind of building region-dependent objectives into our controller. We can build in region-dependent disturbances as well. So here we added, we have a quadcopter basically in 2D, and we added wind in different regions. So what you see in the left is when there's no wind, your vehicle just kind of goes to the left around this obstacle. When there's wind, but you don't know about it, right? We added like this tornado in the middle, right? And that tornado blows you into the obstacle, right? So there you crash. And then if there's wind and you know about it, the vehicle actually goes the other way around that obstacle to kind of go with the tornado, right? And it avoids the obstacle and gets a nice fast solution, right? So we can bed mixed integer representations of disturbances, right? And then we can also have mixed integer models. So to show that, we modeled a fixed wing vehicle just as a unicycle. That winds up being differentially flat, so we can write it with a linear model in a different set of coordinates, right? And then we can impose some velocity and turn rate limits on it. So that's kind of vehicle dynamics. Then because I'm an energy systems person, right, we wanted to have a powertrain that was interesting for this vehicle. So we made it a very simple model of a hybrid powertrain. We can pull power from an engine, use it to charge a battery, or we can use the battery to power the propeller. And then we tied those two models together, just tying together the power from the powertrain to the motion dynamics of the vehicle, again with some conservative relationships between the velocity and the power. And we pose this problem where there are regions on the map that you can't go into at all, which are these gray areas. But then there's also what we call noise restricted areas. So that's a region where if you want to go through them, you have to turn off the engine and run on battery power alone, which means if you enter that area, you better have enough battery charge to get out of it, right? And so that, again, forms a mixed integer constraint in our optimization where there are regions of the map that impose binary constraints on our model, right? When we're in a noise restricted region, the engine power has to be 0. And you can see it kind of performs as you'd expect, right? It chooses to go through the smallest noise restricted region. It pre-charges the battery and then uses the battery when it's in that area. And we can combine all these things, right? So we can add wind to this, right? So now we have like a wind current here, right? And if you add that wind, the vehicle will choose to spend longer in the noise restricted area, but it's getting helped out by the wind. right? And we can combine risks and battery constraints, right? So now we give the system basically a terminal battery requirement, maybe navigating to some waypoint that's part of a longer mission plan. So if you tell it that it has to end up with a state of charge between 0.9 and 1, then you can do a nice job of avoiding these regions of elevated risk. But if you make the terminal battery charge constraint a little tighter, right now it has to end with a little more charge, it'll choose to do that by taking a slightly riskier path, right? So the big takeaway is we can embed constraints in terms of or we can embed, let's say, binary conditions on objectives and constraints and disturbances all within our mixed integer formulation. So that was all a motion planner, but that's really not enough for an autonomy stack, right? You'd like to also have a higher level path planner that gives you some waypoints as part of a longer mission, and you need some lower level controllers as well. So we went ahead and embedded our motion planner as part of a stack like this. And the problem setup here is our long-term planner is going to use what's called a medial axis planner. It's a graph-based planner. And so it's kind of trying to stay like on average furthest away from the obstacles, right? Going through the middle of corridors. And so it might give you a path like this to your goal. But then we also sprinkle in some obstacles that planner doesn't know about, right? So these are obstacles that your graph search algorithm you run in advance doesn't know about, but you detect them as you drive. And in this case, it doesn't make a difference, right? Because our graph plan just happens to not intersect with any of those unknown red obstacles, right? But in some case, it will make a difference. And so about 6 weeks ago, we got our test bed delivered to Penn State where we can actually do some experimental validation. So I'll show you some videos now. They might look a little rough, but give me a break. We've been working on this for a month and a half. But I think it's really good progress so far. So we have a motion capture system that just gives us positional feedback. We have a raw spot that'll be running in. These are in a brand new building on Penn State's campus. That's called eCore. And so here what we're showing is kind of a overlay of the virtual obstacles on top of our hardware looking from overhead. So you can kind of see there's a real robot down there, and then we put a red box over top of it just to make it easier to track. This black line is the graph-based motion plan. And so this avoids the blue obstacles that it knows about, but it goes right through some of the red obstacles that it didn't know about. And so the goal of our MPC motion planner is to follow, in general, the graph plan, but along the way, locally, avoid these obstacles. And so we do that by using MPC. We have our prediction horizon there, and then we give it a terminal constraint that is along the path of the graph planner. And so if we run this, you'll see our robot does a nice job of following, obeying these terminal constraints and staying on the path that the graph search generally asked for, but it also will deviate from that path where necessary to avoid obstacles. So I know a lot of you are roboticists. You know a lot about path planning and following, right? I'm sure more than I do as someone who's kind of new to this particular application. But we think we have a nice tool, right? These hybrid zonotopes could be a good tool for solving these problems. And this is really a first application, hopefully on the way to extending it to more general applications. Here's another one where one of our unmapped obstacles basically cuts off a whole corridor. So the graph planner wants to go this lower route, but there's an obstacle there, and we're going to wind up not being able to pass that at all. And so we detect that that's happened, basically because this terminal set will go infeasible. And then we request a different route from the graph planner that uses a different corridor. So if you watch closely, right, it'll kind of try to go past this obstacle, but then we can't track that terminal constraint anymore, and it jumps to a different path. And that's when we asked our graph search algorithm to run again, but exclude this corridor because we decided that corridor wasn't passable. And we can basically just keep doing this anytime we get stuck until we either reach the goal or try all corridors in our graph search. So this is like literally a video that my graduate students created yesterday, right? Very new work, but hopefully shows we're on the path to some neat things. We also asked ourselves whether we could solve a dual problem in estimation, and it turns out we can, right? So we have now a mixed integer moving horizon estimator, which is the dual to a mixed integer model predictive controller. So for this, we took elevation data local to us in Center County, and we made a hybrid zonotope approximation of the terrain. And then we took some flight data and tried a couple different estimators to try to estimate the position of the vehicle using corrections based on the height above the mountains, right? And so, we tried a dead reckoning approach that's basically just integrating over an IMU, right? That does pretty poorly. And then we have a particle filter and we have our mixed integer approach. And so we wind up getting about half of the RMS error of a particle filter, where that filter had 10,000 particles, right? And our approach, solving a mixed integer program, but it takes us about 41 milliseconds on average to solve that, right? So it winds up being pretty efficient. I think the last slide I'll present here, just some other things we're working on. So continuing to do this testing, like I said, this is very new to us and to me. So we're continuing to grow our experimental capabilities in this robotic space. And then looking at more general problems. So what I showed you is how we can exploit some of the structure and context of a path planning problem and a motion planning problem with hybrid zonotopes. But what we found just in the last couple months is that we can actually exploit structure in much more general optimization problems that involve constrained or hybrid zonotopes. And we're looking to write some papers on that, and we'll also release some nice packages compatible with ROS2 and Python that allow you to solve these optimization problems in real time on pretty light hardware. We're also doing other things like using hybrid zonotopes for robust control co-design. I just got the alert from Google Scholar that a paper we wrote with Neera Jain at Purdue went live. I think that was yesterday that went up. Doing things like, again, dual problems like estimation. And then we have things going on in our lab that don't necessarily involve set-based methods, right? Modeling control for hybrid electric aircraft and for microgrids, and design optimization for uncrewed undersea vehicles, right? Lots of other fun stuff. I could give an hour-long talk about all of those, but we're out of time. So that's what I have. Happy to take any questions. I do want to acknowledge, of course, lots of great students in my lab working on these things, but also lots of awesome collaborators at other universities. Their photos are there, and of course, you can see them as co-authors on our papers as well. All right, that's what I have. Thank you.
Well, thank you, Herschel. And maybe, are you able to see the chat in Zoom over there? Just want to make sure that we don't miss out on any questions from the remote audience.
Yep, I don't see any questions in the chat.
So questions from the live audience then.
With a rich talk, and there's a sea of information to go over.
Yeah.
I guess I have two main questions. When you're doing backward reachability with hybrid zonotopes, do you face the problem that is faced in constrained zonotopes where you have to resort to inner or outer approximations, or is this something that you can do in closed form, or at least like you have good approximation?
Yeah, that would be a challenge, right? So when we can represent sets exactly, it's easy to do backward reachability. When we have approximations, that gets tougher, right? And so yeah, that's a good point and observation. Yeah, when I talked about backward, that was all in cases when we can represent those mappings exactly.
So in the general case, it's still a challenge for hybrid zonotopes.
Yeah, if you have a nonlinear system that you're approximating, it would be a challenge. Yeah.
The second question has to do with this video. I'm just interested in what kind of like tuning went into this, because this moving target, if it's way beyond your MPC horizon,
yeah,
where you're going to be able to track it. So like, could you talk a little bit about what kind of tuning went into making this work?
Yeah, so you're definitely right that there's kind of an art in I don't know why there's kind of an art in like picking how you choose this terminal waypoint along the trajectory of the vehicle. Like I said, like this video literally was taken yesterday night in our lab. So I don't know that we have a great answer for that yet. I could try to tell you about the method we're using, but I don't think it's necessarily the best method. So like I said, we're now that we have something running, we're starting to write up the papers on this. give us a couple months. We'll put that paper on archive and you can see what we settled on. But that is definitely the challenge, right? That would determine, for example, like, do you decide that you can't get through a corridor because it's actually not passable, or maybe just because we are too aggressive in trying to track the right? Like, there's definitely considerations there that I don't think we've fully fleshed out yet. Yeah.
This is a very impressive collection of results here. One thing that I must have totally missed is so when you're constructing the zonotopes, in order to go from the box constraint to the zonotope, you've got a matrix multiplication, then you've got a shift, right? Is there a systematic process for generating the transformation matrix and the shift on a problem by problem basis? Or
Generating, so like,
where does that transformation come from in order to get to the zonotope representation that's coming?
I see. Yeah, there are like standard algorithms for, let's say you give me a polytope and half space representation and say, give me the constrained zonotope version. There are standard methods for doing that. A maybe related question is like finding the minimal representation, and that can be tough to do, especially for hybrid zonotopes. But finding a representation is fairly standard to do.
Okay.
Yeah, I think there's a chat. So there's a question in the chat about, can I explain the intuition that hybrid zonotope reduces time complexity? So that's a good question. So one way I would think about that is, again, hybrid zonotopes allow you to embed like an exponential number of polytopes, right, with just a linear number of binary variables. The time where that bites you is where you have to solve a mixed integer optimization over those binary variables, right? So mixed integer optimization, right, can be NP hard, but in practice, because branch and bound algorithms and heuristics have gotten really good, in practice, it's not that complex necessarily. And so that's where we really see benefits, as opposed to trying to directly propagate and evaluate all of those exponential numbers of polytopes, right, which would definitely be complex to do computationally. Hopefully that gives you some intuition for it. Yeah.
Just to make sure I have the right mental model. Suppose I start with, I want to just do the forward reachability. I start with an initial set. It's described by one of these hybrid zonotopes. Then I propagate forward one step, propagate forward another step. That's easy. Like those are the basic operations that you have. Now I get to the final terminal point. I say, well, what is this set? I want you to tell me, like, what are the vertex representation or something else. That final thing is going to be the hard thing to say. Like, is that the right mental model I should have?
Yeah, like we can basically build all the matrices that describe that set, right? But now you want to know, like, does that set intersect some unsafe region? Well, now we have to kind of explicitly understand what that set is, not just implicitly propagate all the variables for it, right?
Moving forward with linear dynamics is easy, but doing set intersections with unsafe sets, that's the more difficult.
If you want to know if those intersections are empty, for example, right? Now you're going to solve some mixed integer programs. And again, it's not just pushing forward with linear representations, right? It could be switched or, you know, hybrid. It could involve logic, right? If-then type of statements, right? It's pretty expressive class of systems we can propagate. But in the end, right, like evaluating answers is going to, you can't go the whole way through to getting an answer without solving some kind of optimization problem along the way, usually. Yeah.
Very nice talk. So for the still on the what do you call it, hybrid zonotopes, right? So on the numerical examples you gave, I understand it's more. I would prefer to name to call it like a switching system from the So for the difference between switching system and hybrid system with impulsive state change, there are some I see some differences. Do you think you might add some more comment or lemma theorem when you really dealing with impulsive hybrid systems?
Impulsive hybrid systems.
Yeah, you have like impulsive state change.
Yeah, I think that would be. So maybe another way to frame it would be if you had a system that you described in continuous time instead of discrete time. Is that what you mean by the impulsive? I'm not sure what you mean specifically by that term.
Like when your state hits some, let's say your card, and then it suddenly jumped onto some.
Right. Yeah. So that is that is a challenge, right? We're kind of getting around that kind of, like bouncing ball type problems, right? We're getting around those by using a discrete time representation of the system, right? If you model the system in continuous time, that's where, you can impact at any time. If you go back to that example I showed with the thermostat, right? Like we're updating in discrete time. So sometimes you go past the temperature bound, and then the next time you're due for an update is when the thermostat switches. So a lot of systems actually do update in discrete time like that. There are ways to take a discrete time reachability and kind of get the continuous time sets by basically bounding the inner sample behavior. You like bloat the set based on what the inner sample behavior could be. So there are approaches to doing that. We haven't really looked into those much for hybrid zonotopes yet. So we're kind of choosing our plants and our controllers to all be in discrete time. And that is, a simplifying assumption for sure.
Right, so we're at 4:34 right now, so I would invite people to talk to Herschel if they've got more questions, but let's thank Herschel again. And please feel free to hang out and talk to Herschel or talk amongst yourselves or grab some cookies and not talk to anyone. Whatever. All right, so I've got 2 reservations in place right now. So I got one for Grizzly Peak at 6:15, I think, and then I have by 8 o'clock at but I think we don't want to wait until 8 o'clock.
I can see it.